Hello, Dr. Bhatt here. Welcome to all of our students, friends, and learners in chemistry. Today, we introduce to you another video lecture related to solutions. The topic has already been taken up or started earlier. And this chapter is in continuation to what we have already taken up. Let us see what is there for us. Now, we shall continue with our earlier topic, solutions, wherein we had taken up solution of gases in water. That is Henry's law and related concepts. Now, today, we shall take up another unit of the related chapter, and that is liquid-liquid solutions. Solutions of two liquids. Liquids also get mixed up with each other, but there are number of liquids which do not get mixed up. They do not form a solution. They remain heterogeneous. As we know that we term a solution when the components which are being mixed become homogeneous. So there are a number of liquids which, when mixed together, become homogeneous. Homogeneous means it's difficult to trace them out within the mixture. Both the components of the mixture, which are liquids, they become a true solution. Now, since we are concerned with liquid-liquid solutions, therefore, I'll advise you to recall certain concepts about liquids, because the solution which we get, the solution which we prepare by mixing two liquids, again is a liquid. Solution itself is a liquid. Therefore, it has properties related to the mixed liquids, or in general, the properties of the liquids. And the topic is not new to us. We have learned about various characteristics of the liquids. Then, before we get into the main characteristics of the solution, liquid-liquid solution, it is desirable to get or review some concepts about solution, about the liquids. Liquids are of two types. What are the topics we are required to take up in this connection? We shall hurriedly go through them and revise whatever we have learned about the properties of the liquid or the characteristics of the liquid. There are, in this context, I'll say two types of liquids are there, miscible and immiscible liquids. Those liquids which get mixed up and become homogeneous to form a solution are known as miscible liquids. Why they get mixed up? Why they are miscible? We have to understand. And then there are a number of liquids which do not mix up. Rather, they remain separate in spite of best efforts. They remain heterogeneous. They fail to get mixed up. They do not prepare solutions. Therefore, these are known as immiscible liquids. What are the reasons? We have to take up again. Then, one of the important properties of liquid is vaporization and evaporation. Vaporization and evaporation are the important characteristics of a liquid. Vaporization, what is vaporization and what is evaporation? We have to take up again and review our concepts. But during this process, there comes into existence, and we need to understand it, that is vapor pressure. What is meant by vapor pressure? What is the difference between vaporization and evaporation? In a broader sense, it appears that vaporization and evaporation are the two similar terms, but still there is a difference. What is that difference? We have to understand. Then this vapor pressure or vaporization or this characteristic property of evaporation affects other important property of the solution, and that is boiling and boiling point. What is boiling? And what is meant by boiling point? We have to understand a lot of it. And then freezing point. A liquid, when cooled at a particular temperature, depending upon the nature of the liquid, it turns to a solid. Needless to point out that these are phase transitions. A solid can be converted to a liquid, and liquid can be converted to a gas. So liquid is an intermediate step. When liquid is cooled down, an equilibrium at a particular temperature sets in and it turns to a solid. Similarly, it gets evaporated or vaporized or into a gas having its own pressure. So what are all these? We need to revise it, and we shall quickly go through it. After that, we come to the main topic, which explains the characteristics of liquid-liquid solutions. That is Rault's law. What is Rault's law? It's mathematical derivation and certain other concepts we need to understand. Then, of course, we have to go through a molecular or interparticle interactions in the liquid and also in the solutions. So let us take up and review the properties of the liquid first. Now, just as I pointed out, there are two types of liquids. One are such the composition or the structure or the molecular structure is such that the liquid gets mixed up. It becomes homogeneous. So, such liquids are known as miscible liquids. Suppose there is a liquid A and liquid B. If you mix them together, they become homogeneous. It's not possible to separate them by simple methods. So, why they get mixed up? The reason is, it is because of their similar molecular structure. If they are polar means having certain dipole moment. And the molecule having polar nature get mixed up and forms a homogeneous solution. This is known as miscible liquid. A number of examples can be given: ethanol and water, gasoline or petrol. You know, petrol consists of a number of liquid hydrocarbons. They get mixed up and form a homogeneous solutions. Similarly, gasoline, and like that, several liquids are miscible. Apart from that, there are liquids which do not get mixed up. Do not get mixed up in spite of best shaking or making efforts to make them homogeneous. Rather, what happens? They separate into different layers. A layer with lower density or a specific gravity floats over another liquid having a higher density or a specific gravity. Okay. So this is just a representation here. There is a test tube having liquid A and liquid B, and it forms a miscible liquid. In the other case, there is a immiscible liquid. Liquids with different polar nature do not get mixed up. Wherever there is a difference in polarity, they do not get mixed up. Similar polarity is there, they will get mixed up. Examples well known to us: many vegetable oils and water, they never get mixed. Chloroform and water, and several other examples we shall come across. We know about it, and we have to take up. We have to identify which are miscible liquids, which are immiscible liquids. You get questions based on it. So, next property of a liquid is volatility of a liquid. A liquid has a characteristic which makes them to turn into gas even at room temperature. At room temperature, need not boil it. Suppose there is certain volume of liquid, any liquid, say water. When it spreads on our floor or any surface, after some time we find that the quantity of water goes on decreasing, reducing, and finally it disappears. Why it disappears? It is because of their volatile nature. Liquids are characterized by their fluidity and volatility also. Fluidity means they have a tendency to flow. Wherever the liquid splits, it easily finds its own way depending upon the slope. And at the same time, starts evaporating or vaporizing. So, what is vaporization? Vaporization is a process occurring at a temperature below the boiling point. Every liquid at a particular temperature boils. Now, what is boiling? We shall take up a little later. But then, if it occurs at a temperature below the boiling point, it is known as vaporization and also evaporation. It's two very similar terms, and we commit mistakes to understand it. When we shall use evaporation, when we shall call vaporization, there is a difference. We shall take up a little later. And this, for example, we know that a liquid which has got a lower boiling point is more volatile. A liquid having higher boiling point is less volatile. The tendency of the substance to vaporize or get evaporated at room temperature Take care. Room temperature. Evaporation or vaporization is a process where a liquid turns to a gas. It occurs at room temperature. Okay. Gas, or you can say simply be termed vapor. So, a liquid with lower boiling point vaporizes first. A liquid having higher boiling point vaporizes slowly. And therefore, what I mean to say that every liquid has got different volatility. And therefore, whenever there is a difference in a particular characteristic, we need to measure it. We need to grade it. How do we grade? We grade it in terms of what is known as vapor pressure. Organic liquids, many organic liquids are known to us. Benzene, gasoline, butyl acetate, acetone, diethyl ether, dimethyl ether, and so many liquids, organic liquids are there, which are usually volatile. They turn into the gas easily. They turn into vapor easily. Even if the temperature is much less than boiling point, but at a faster rate. And the rate of vaporization is measured by vapor pressure. For example, there is an experiment, some data is here, where at 25 degrees Celsius at the room temperature, the vapor pressure of water is 0.03 atmosphere. Mind it, whenever we refer a pressure, may it be vapor pressure or any type of pressure, the temperature has to be mentioned. So, vapor pressure of water is 0.03 atmosphere at 25 degrees. And at the same temperature, methanol, CH3OH, methyl alcohol, has got a vapor pressure of 0.36 atmospheres. What does it mean? There's a lot of difference between 0.03 and 0.36. Means that methanol or methyl alcohol will vaporize faster as compared to water. So that is there. Or you can say that methanol is more volatile than water. Not only, and this is an important characteristic. We apply it, we use it. The volatility of a liquid plays a significant role in industrial applications. For example, we have an idea about petroleum distillation. Or we know what is fractional distillation, a substance which has low volatility gets condensed, turns to a liquid easily. A liquid with lower boiling point is converted to a liquid earlier than another liquid with a higher boiling point. Now, this characteristic of liquid is therefore used in what is known as fractional distillation. And using this, we have we process petroleum to get different fractions of it. That is petroleum distillation. Now, let us have some more considerations about vaporization. Vaporization is a phase transition. Phase transition means conversion. It's a physical conversion, physical change. No chemistry is involved here. Of course, at a particular condition, an equilibrium may be set. An equilibrium is established. It occurs I have already given you, at a temperature below the boiling point. And very important, the term vaporization is closely related to the space under which it occurs. In a confined space, limited space. Suppose you take water in a container or alcohol in a container, then it will gradually turn into vapor. And the process is known as vaporization. Means you have taken in a confined space. So, but what is evaporation? Evaporation, there is a little difference. Evaporation occurs in an unconfined space, open area. Suppose water splits over here in the room, in your room, and you don't say it gets vaporized. We say it gets evaporated because it is an open space. But the same liquid, if taken in a container, will also form gases, will also turn into gas easily. But this process is known as vaporization. And when both of them occur at a temperature below the boiling point. Below the boiling point. It may be any temperature. So, and vaporization does not depend, rate of vaporization does not depend upon the surface area of the liquid. Depends on the temperature of the confined space of the surrounding liquid. What is the temperature? Of course, it will be below the boiling point. If the temperature is more, the rate of vaporization increases. Obviously, why does it increase? We have to get an idea, and we shall take it up a little later. Now, what is vapor pressure? Just I have given you an idea what is the vaporization and what is evaporation, what is the difference between the two. Both are phase transitions. One occurs in a confined space, that occurs in an unconfined space, means open area, and both are surface phenomena. Now, why a liquid gets vaporized? Before we discuss anything about vapor pressure, let us understand why a liquid gets vaporized. Suppose there is a container and suppose there is a container in which we have taken certain amount of liquid and it is open. It is not closed. It is open. What will happen? We know that the liquid molecules are not they are not stationary. The particles of the liquid are in a constant motion, rather they collide with each other. And as a result of their collision, there are certain particles which move up to the surface. And the collision depends upon temperature. The rate of collision depends upon temperature. Those particles which rise up to the surface, they get striking pressures from the molecules below or from the particles below in the liquid. And therefore, they have a tendency to escape out, to get out of the liquid. And if there is an open space, not closed, mind it, the figure represents a closed space because we have to discuss vapor pressure. But had this been open, what would happen? All those particles in the gaseous forms will get out. And that process is known as vaporization. Occurs in a confined space. Now again, suppose, take another case. I close it with a tightly fitting lid, some type of cover which is sealed. and there is a liquid here. There is certain space left over. So what will happen? The gas particles, the liquid particles will rise up, leave the surface, strike over the walls or walls of the lid, because they don't find any space to get out. They will get condensed. They will turn to a liquid and again drop over the liquid surface and mixed up. But this process continues. It occurs all the time. But after some time, what happens that the particles which are getting converted to liquid are those particles which are condensed, vaporized particles, gas particles, which gets cooled down and turned to a liquid, and those particles which are leaving the surface and turning to a gas, their rates become equal. And we know that in any opposing interactions or chemical reactions, may it be physical or chemical, if the rate of opposing reactions or interactions are similar, an equilibria is established. Immediately after some time, an equilibria is established here under the condition that the liquids particles are not permitted to get out and they get condensed. So, mark the condition. And in this state, whatever pressure is developed by the gas over here in the closed container, that is known as vapor pressure, depending upon the temperature, of course. So we can state vapor pressure as pressure developed by vapors of the liquid in a confined space, most important, and is termed as vapor pressure at a particular temperature. Pressure has got a relation with temperature. So that is there. So all this is described here. You may go through it carefully. An equilibrium is established only when the rate of vaporization becomes equal to rate of condensation. Since the rate of vaporization is temperature dependent, the vapor pressure there is a direct relation of the vapor pressure with the temperature of the surrounding space. Next, let us see what is there. Vaporization, vapor pressure, and now evaporation. What is evaporation? I have given him an idea earlier also, that vaporization is a phase transition, evaporation is also a phase transition. And the same process occurs. Liquid is converted to a gas, but an equilibrium may be established after some time. And here also liquid is changed to a gas. Both are surface phenomena. But this occurs in an unconfined space, open space, not closed. And this occurs in a confined space. And similarities are there. That is why we commit mistakes in recalling them. Vaporization and evaporation. Sometimes where we need to call evaporation, we need to term the process as evaporation, we call it vaporization. Wrong. If it is an open space, it is evaporation. If in a confined space, it is vaporization. Both occurring below the boiling point of the liquid at a temperature below the boiling point. And then in this case, an equilibrium is established, whereas in case of evaporation, equilibrium is not established, but it will continue. How long? Till the atmospheric pressure of the surrounding space, that is atmospheric pressure, becomes equal to the evaporated vapor pressure of the gas that is there. So I have given you all these points of differences in tabular form. Next, we have to take a very, very important characteristic of liquid, that is boiling point. And mind it, this boiling point is of much use to us so far as our subsequent studies about solutions are concerned. How the boiling point is affected, how the boiling point of a liquid is affected in solutions, how the vapor pressure is affected in solutions. When the liquid gets mixed up, there is a change in vapor pressure. It is not same as it was with the liquid, pure liquid. So is the case with boiling point and also freezing point. So all this we are going to take up gradually in subsequent studies. Now, whatever I have given you regarding vaporization, you see here, this is an open container. Container is there, but it is open. All this we have discussed. Earlier, the diagram showed, represented a closed container, because there the topic was being discussed was vapor pressure, vaporization. It is only an illustration here through diagrams. A number of particles are there, a few particles are shown rising up, and escaping tendency is there. Escaping means getting out. They have a tendency to leave the surface, leave the liquid level. And as one particle gets out, the other particle comes over this, the surface and tends to get out in form of a gas. So this is known as vaporization. Okay. Now, boiling is something different. Boiling occurs when the liquid is provided energy. And the common form of energy which is provided to a liquid is heat energy. Just heating. Take a bulk of the liquid in a container. You have to take, if you have to boil a liquid, you have to take a container. And the liquid which you take in a container, that is known as liquid bulk, or bulk of the liquid. It may be 1 liter, it may be 2 liter, it may be even more. So the bulk of the liquid is taken and heat is provided to it. Heat it by any source. So what will happen? This heat energy results to make all the particles present in the liquid more active. They become kinetically more active. They move faster. Why? Because they get thermal energy. We are providing heat, the molecules utilize this thermal energy. We understand what is thermal energy. We have already discussed in class 11. So, even though I am heating it, we are heating it, we are increasing the temperature here, then gradually the particles of the molecules of the liquid gain this energy in form of thermal energy. And because of increase in their thermal energy, they becomes more kinetically active. They move faster. This energy is converted to kinetic energy. And their escaping tendency becomes more, greater. It goes on increasing. And not only this, at certain stage of time when the temperature is more, at a particular temperature, there is a turbulence in the liquid. Turbulence means disturbance. All molecules get disturbed, they start moving faster, and their escaping tendency becomes more. Goes on increasing. Not only this, there is a competition, I'll say, between the molecules to get out. And during this competition, the gaseous forms, the molecules in the gaseous state start forming bubbles within the solution itself. So, please note, boiling is a process. It's not a phenomenon. It's a process. You apply heat, and it's a process where the liquid gets becomes more turbulent. Turbulence means some type of disturbance between the molecules. You can see it boil. The liquid is boiling. We easily realize some disturbance within the liquid, and particularly at the surface. And not only this, even in the liquid bulk also, bubbles are formed, and the vapors are the gas which is formed. The liquid starts boiling along with evaporation. So that is boiling. But this occurs faster at a particular temperature, which depends upon the nature of the liquid, structure of the liquid, molecular structure of the liquid. Water has a boiling point at 100 degrees Celsius. Alcohol is boiling point of about 78 degrees Celsius. And similarly, every other liquid has got their own boiling point. Acetone has a boiling point of 56 degrees Celsius. So, based upon this, we now understand what is boiling and what is boiling point. All this is provided over here. And then the temperature at which liquid boils is known as boiling point. And when this continues, it continues when the pressure of the evaporated gas, evaporated liquid or gas becomes equal to the atmospheric pressure, maybe more also. But just boiling occurs till a particular state, particular stage, a particular condition. Only then bubble formation and continuous escape of the molecules will occur in form of vapors or gas. Okay. So that is boiling. If the pressure of the gases which are being formed is less than the atmospheric pressure, the vapors may escape, but boiling won't occur. There won't be any turbulence within the liquid. There won't be any bubble formation in the bulk of the liquid. So that is boiling. Now, this is a character, and it depends upon molecular structure and the atmospheric pressure of the gas. It's a bulk process. It's not a surface process. Vaporization and evaporation was a surface phenomenon, but this is a bulk phenomenon. Now, we come to the main topic. Till now, we have just reviewed whatever we have learned earlier. But what will happen to vapor pressure in a binary liquid solution? Liquid gets mixed in liquid, and you get a homogeneous mixture, and that is known as a solution. And binary means two components. There can be many liquids mixed together, but we need not go into those details as per our studies. We need to learn binary liquid-liquid solution. What will happen to the vapor pressure? And actually, the vapor pressure of the solution, which itself is a liquid and contains two components, both are liquids having different boiling point or different vapor pressure. So vapor pressure of the liquid solution is not the same as those of the liquids, pure liquids. One liquid may be having certain vapor pressure, the other liquid might be having its own vapor pressure. And as we know, it depends upon the characteristics of the vapor pressure. So the vapor pressure of the solution is different from the vapor pressure of the liquids mixed in the pure state. Liquids in the pure state have their own vapor pressure. Now these liquids, to make us convenient, we'll say they are components. Two component system of a miscible liquid. Miscible should be there. Two components should be there. We may call it as component A and component B, or we may call it as component 1 and or component 2. Though solution exerts a vapor pressure which is different from the individual vapor pressure of both the components in the pure state. Vapor pressure would be now, when there's a, we have already learned in class 11 or earlier that when there is a mixture of gases, each gas exerts its own pressure. And the pressure due to a particular gas or component is known as vapor pressure in the mixture of gases, and at the same temperature. The gases should be non-reactive. Well, that we have learned in case of Dalton's law of partial pressure. Okay. This partial pressure depends, partial pressure in this case, partial pressure of the vapor, depends upon the amount or quantity mixed in the solution. This quantity is not taken as liters, grams, etc. No, we don't use it. Even though we may mix 1 liter of alcohol with 100 liters of water. So that is an experimental view. But for our studies, we have to use a term known as mole. Moles. What is mole? It is well known to us. And we also know what is known as mole fraction. But to recall, I'll say that mole fraction, its a fraction means out of 1. Mole fraction means total number of moles of one component upon the total number of moles present in solution. How many moles of component 1 is there and how many moles of components are present in solution? Mind it, solution contains 2 components. Components means the parts, the liquids mixed up. And these are termed as components. We call it as components. And it's a ratio. A number of questions we have solved lost. Now, to our help, thanks to French chemist Franco-Smart Rault, he has experimentally observed, noticed certain data studied it and given his own law. That is very significant for us so far as these studies are concerned. That is known as Rault's law. For a solution of volatile liquids, the partial pressure of each component in solution is directly proportional to its mole fraction. Very simple, very easy to understand, but a suitable concept is very essential. Sometimes you get a direct question, which of the following statement relates Raoult's law? This states Raoult's law. Are similar questions like that. So, Raoult's law talks about partial pressure of vapor, not the pressure. Partial pressure of vapor in a solution. And when we say partial pressure, we means there can be certain number of gases present in the mixture. Now, of course, in this case, since we have taken binary liquid-liquid solution, there are two components. Both of them, the vapors of both of them will be there. So the partial pressure of each component is directly proportional to its mole fraction. How many moles we have mixed out of the total number of moles present in the solution. So you have to learn it. Now, this can be represented mathematically also. With certain simplification, we can arrive at a particular conclusion also. We can infer something about it. Raoult's law in a binary liquid-liquid solution. Mind it. Binary liquid-liquid solution. So we have seen that vapor pressure is effective in solution. Vapor pressure of a liquid is not the same as it was there in the pure state of that liquid. So let us derive it mathematically. We can write Raoult's law because there is a direct relation. We can represent Raoult's law for two components A and B. Mind it, he has used a term volatile liquids also. Volatility is the characteristic of a liquid, and it is very much observed in case of liquids which are more volatile. So that's why volatile liquids have been used. Let there be two component A and B. You can call it as 1 and 2 also. We continue with say component A and component B. Component A means a liquid having its own name, maybe any liquid, we call it as A liquid. The other liquid is B. So according to Raoult's law, partial pressure of A is proportional to XA, direct proportion. PA, please mark how we have written partial pressure. P, small letter, A as a subscript. Sometimes, in many cases, in certain other literature, P can be capital letter also, but A is always a subscript. Partial pressure of A is directly proportional to X represent the mole fraction. Not moles, mind it, mole fraction. How many moles of A are there out of the total number of moles present in the solution? Similarly, PB is equal to XP. A and B identifies the component. Here we can apply Dalton's law of partial pressure. Dalton's law states that since there is a proportionality, we can use a constant over here and equalize. What is that constant? This constant is the vapor pressure of the pure liquid A. component A in the pure state. What is the vapor pressure of the component A in the pure state? Although it is a constant, but this constant is referred with reference to the type of liquid, structure of the liquid, characteristic of the liquid. It's not a universal constant which can be used anywhere. It is written as P not A. Similarly, for component B or liquid B, we can write it as P not B. Now, these are the pure state, pure component. Then what will be the total pressure of the solution? That will be equal to PA plus PB. Means if the vapor pressure is known, partial pressure is known, we can find out the total pressure, vapor pressure exerted by the solution. Partial pressure has to be known. Now, to make it more easy for us, convenient for us, we have made certain simplification, mathematical simplification. It should not be very difficult to go through it. P naught A, we have just substituted here. PA, we have substituted P naught A. PB, P naught XP. And it is known that now this A and B, different mole fractions, need to be rather simplified. We can convert A, change A, number of moles of A, in terms of number of moles of B. We know that total number of moles fraction is equal to 1. Fraction, a fraction means out of 1. So, XA will be equal to 1 minus XB. And we substitute it over here in this state and in this expression and simplify, we get that total pressure will be equal to pure pressure of component A minus the difference P naught B minus P naught A, difference between the pure components multiplied by the mole fraction of XB. This is known to us. We know the vapor pressure of the pure component, both the components, vapor pressure in the pure state, and we also know the mole fraction of XB, which is present. This can be simplified in terms of XA also. You get the same result. Now, here are the certain conclusions. Certain conclusions out of what we have done. There is a linear variation in the vapor pressure of the solution in terms of number of moles of component. Whatever we have discussed is here. Vapor pressure of a solution, XA is equal to 1 or XB is equal to 1, the vapor pressure of the pure liquid is represented. XA1 means there is nothing else than XA. It is pure. XB is 0. Mole fraction of component B is 0, means A is pure. So, that vapor pressure of the pure liquid is represented. Vapor pressure of a solution may increase or decrease. Very important here. This third point is very, very significant to be understood. The vapor pressure of the solution may increase or decrease. It may increase also, it may decrease also, depending upon the number of mole fraction of any one component and also its vapor pressure in the pure state. Any one component, maybe A or maybe B. Total vapor pressure is sum of the partial pressures. So, and the total vapor pressure of liquid can be expressed in terms of vapor pressure of each component, particular composition. So that is what we have derived. Okay. So this can also be shown or represented through a graph. It becomes very simple to understand. The only thing is we need to study the graph carefully and a number of times to make you confident. Simply going through once may not be very much effective for the sake of learning. You have to study it carefully, draw it carefully, solve it, the related problems carefully. Because in your questions or problems, you get a graph drawn like this, and a number of questions are asked. So this has to be understood carefully. Look here, it's a simple graph having x-axis, y-axis, but there are two variables. It is a graph between vapor pressure and the mole fraction. Mole fraction of both the components. Both the components. Mole fraction of A and mole fraction of B. These mole fractions are considered as variables for the solution. Solution which you prepared, it may have any number of mole fraction of a particular component. Therefore, we have to draw a graph in such a manner showing both the variables. Y-axis representing pressures, vapor pressure. X-axis, mole fraction. X-axis for component A starts at 1. And as we move further, it may be 0. Similarly, just opposite to it, because we are studying solution. Opposite to it, xb may be 1, and at the other end of the graph, of course, x-axis, it will be 0. So what I mean to say, as the mole fraction decreases, something happens to the vapor pressure. As the mole fraction increases, something would happen to the vapor pressure. The pressure would change. Something means it will alter. So how does it change is represented in this graph in terms of mole fraction of A and B. And when it is drawn experimentally, we find for component B, partial pressures. This PB represent partial pressure, because here it is a solution in between the graph, the vapor pressure, the solution is found. So PB, B goes on increasing from 0 to a point when it becomes mole fraction is 1. When it is 1 means no XA is there, no A component is there. And this vapor pressure represents the vapor pressure of the pure liquid B. Whereas in between, this represents partial pressure at any stage. At any stage. Similarly, for A also, as the mole fraction starts increasing from 0 to 1, it goes on increasing. If you look at the other way, it goes on decreasing. Now, this is with relation to the vapor pressure. With the mole fraction, we can find out the total pressure P by just adding the partial pressure of PA and PP. We can find out the partial pressure of PA and PP here from the graph and add them. So that gives the total. So graphical representation is very important. To make us more convenient, we have drawn this with green line, and the other one is representing the total pressure is given with black line, dark black line. Green line represents, of course, it is a straight line. The reason for being a straight line is that there is direct proportionality between mole fraction and the vapor pressure. As stated by Rault, there will be a straight line. Okay. So all this is described over here. You need to learn it several times and make yourself confident. Next, we have to take something more. What will happen to the composition of the vapors? What would be the composition of the vapors of the solution? The solution, when vaporizes, also has two components in the gas, vapor of component A and vapor of component B. Both of them exert their own pressures. So it is, in a way, it is a mixture of gases, mixture of two gases. And then, therefore, Dalton's law is applicable. We need to know about the partial pressure of component A and the partial pressure of component B. Again, according to Dalton's law, just given in a statement here, that the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the partial pressure of individual gas. P partial, simply partial pressure. Any component is equal to total pressure multiplied by the mole fraction of that component. Component 1 we may call it component A, doesn't matter. Now here in this case, in our binary solutions, the vapors have their own compositions, vapor of the solution, I mean, their own component composition, and let it be, say, the number of mole fraction A be represented by YA and component B be represented by YB and the total pressure be P total. Therefore, partial pressure of A will be equal to YA into total pressure. It has to be different than what it was there in the solution. And that's why we write here as Y. That's why we have to represent it with the letter Y, YA and YB. So sometimes, rather very frequently, I'll say, you get questions on composition of the vapor in binary liquid solution. You need to understand Dalton's partial pressure, calculate mole fraction of different components, and get the partial pressure. Finally, we have to get an introductory idea, I'll say, not the detail today. We shall get into more details later about what is known as interparticle or molecular interactions in solutions. In solutions which we have prepared or which we get, there are interactions between the particles. And what are the particles? Molecules. Mostly, these molecules are in a state of motion. They are not stationary. They are not idle. They keep on moving within the bulk of the solution. So these molecules have their own attractive and repulsive forces and interact with each other. Interact with each other. Interact means no chemical reaction, mind it. No chemical reaction occurs. Okay. Simply a physical combination. Unite. Molecules get united. Okay. That is known as an interaction, physically. So, in the pure liquid A, let us see what happens in the liquid A and liquid B. If the liquid A is there are molecules of A, we call it as A molecules. And a number of A molecules are there. There are interactions between AA molecules. We call them as, for our convenience and studies, we call them as AA interaction. Similarly, such interactions are there in liquid B. We call it BB interactions. BB interactions. Now, what is there in the solution? In the solution, both the components are there. They have formed homogeneous solution. They have got mixed up. So here what happens? There is comes into play another type of interaction. That is between the molecules of A and B. We call them AB interactions. So three types of interactions are occurring in a solution, where in the pure liquid there is only one type of interaction. Now, in the solution there is a AA interaction, BB interaction, and AB interaction. What is interaction? We have just discussed. Take care. And then, in spite of all these interactions, they become homogeneous. There is a condition for homogeneity and situation when a good solution forms. Good is just a broad term. A true solution or good solution, it's only a broad term. Actually, these interactions, if they are of the same type, if AA interaction, BB interaction, and AB interaction are of the same type, same interactions, whatever interaction is occurring in AA, whatever interaction is occurring in BB, and whatever interaction is occurring in AB is similar, then a solution is formed which obeys Rault's law under all conditions of concentration. Whatever may be the dilution or concentration of the solution, Rault's law would be obeyed, would be followed. But all the solutions do not follow Rault's law, even though the solution may be there. Even though we may get the solution, but it may not be followed Rault's law totally. They may be closer to Rault's law, but there may be a difference. And such solution which follow Rault's law under all conditions or range of concentration is known as ideal solution. Use the term ideal, not the true, not the good solution, fair solution, no, ideal solution. But those solutions which do not follow Rault's law under all range of concentrations, they are known as non-ideals. And even though the solution is there are deviations from the Rault's law. Deviation means a little difference. If there is a much deviation, there won't be a solution found. And an ideal solution, formation of an ideal solution, is possible only when their molecules have similar size, shape, and molecular structure. If the molecular structure is same, size is also same, and the shape is also similar, then an ideal solution. There may be liquids which get mixed up, but they may differ in shape. There may be difference in size. There may be a little difference in structure. So the solution would be formed, but there would be a deviation. They won't follow Raoult's law under all conditions of concentration or dilution. And the most of the solution differ from ideally. Ideal solution, there are certain examples, and a number of other examples are also there. We shall gradually take up in our subsequent study. A few examples are there: benzene, toluene, chlorobenzene, bromobenzene, carbon tetrachloride, silicon tetrachloride, etc. And having explained everything, a suggestion. I advise you, suggest to my students that they must study carefully the liquid solution, vapor pressure, vaporization, and all such details. But before that, the properties of the liquids, pure liquids, must be carefully taken up. We will be back again soon and take up some more units regarding solutions. And these are subsequently connected with our studies here regarding vapor pressure. Thank you.